This lesson is super fast. It's just a definition you need to know. So a function is said to be analytic at a point x naught if you can write a power series representation for the function around that point. That's it. That's the definition. And if you're like, well, that's every function, let me tell you, it's definitely not. Here's the counter example. Take f of x is e to the minus 1 over x. That is a function, and yet you cannot write down a power series representation around x naught equals 0. If you want to, go ahead and try to write the Taylor series. You'll see that you can't do it. So now, to bring this to differential equations, I want you to consider the following linear second-order differential equation written in this standard form: y double prime plus p of x y prime plus q of x y equals 0. So again, it's linear, it's second order, it's not necessarily constant coefficient. We're allowing for these variable coefficients, p of x and q of x. If p of x and q of x are both analytic at a point x naught, then that point x naught is called an ordinary point of the equation. Okay? A point that is not an ordinary point is called a singular point. Ordinary, singular. All right? So to give you an example, take the differential equation y double prime minus 2xy equals 0. Here, your p of x is equal to 0, because there's no y prime term. Your q of x is equal to this coefficient here, negative 2x. And so those are both analytic functions. They both have power series representations. In fact, these functions, p of x and q of x, are their own power series. They're already in power series form. So the point x equals 0 is an ordinary point of that differential equation. I should write that down. X naught is an ordinary point. X naught equals 0. On the other hand, this differential equation here, y double prime plus 1 over cosine x y prime plus y equals 0, our q of x is 1, our p of x is 1 over cosine x. And this is going to fail to have a power series whenever the denominator is equal to 0. So that's when x equals pi over 2 plus or minus n pi, where n is an integer. And so what that means is that at these points, the differential equation, or these points rather, are singular points of the differential equation. Other points are ordinary points. That's important because you're going to learn a technique for solving differential equations with power series, but it's only going to work for ordinary points. All right, thanks for listening.